So, reminder, there is no lecture next Monday, but we will have a makeup the Monday of last week. Okay? All right, so last time we were talking about the fact that when the temperature of optical molasses was measured carefully, it was found that the temperatures were well below what the absolute minimum limit was according to the simple Doppler theory. And this was a big surprise back in the day. And there were a couple of clues as to what was going on. Some of the experiments that were done showed, for example, that if one looked at the temperature as a function of the intensity of the light, that it actually went down as the intensity got smaller, linearly. Eventually, at some low density, it kind of heats up again. So there's some minimum there. The temperature as a function of the detuning from resonance, the magnitude of that detuning. In the Doppler theory, if the minimum temperature is at a detuning that's at only a half a line width from resonance, it's almost on resonance. And as you go farther off resonance, the Doppler limit, the Doppler temperature increases. Whereas here, what was found is that the temperature decreased with detuning. So, there was one other clue, which was that the temperature was very sensitive to magnetic fields. Very small Zeeman shifts made temperature hotter. So all of this was a clue, or a series of clues, that what was important was not just the scattering of photons related to thinking about the atom as a two-level atom with a ground state and an excited state and some detuning from resonance, in which case all of the dynamical time scale here really, in terms of the scattering, depended on the spontaneous emission rate, but that there are new time scales in the problem. And those time scales were associated with ground state dynamics when we have multiple sublevels. So the fact that the temperatures were low when we were far off resonance meant that the excited state was playing less of an important role. What was going on in terms of the ground state was more important. And in particular, what we know in terms of what goes on in terms of ground state dynamics are two interrelated features: light shifts and optical pumping. let's remind ourselves about these two features. So, if I have a atom, then if we had a two-level atom, and we were detuned from resonance by some amount, then we know that there is a AC star shift or a light shift on the ground state that depends on the intensity and the detuning, right? So we have a light shift, the AC star shift, or something called a light shift, that we've studied in homework and in class, which depends on the detuning and the fraction in the excited state, which is the saturation parameter over 2. Right? And that saturation parameter, we said, was equal to the Rabi frequency squared over 2 divided by delta squared plus gamma squared over 4. And if S is, if we're talking about situations where the detuning is big compared to the line width, then this is approximately equal to the Rabi frequency squared over 2 delta squared, and the light shift is over 4 delta, where the Rabi frequency here was related to the matrix element of beta E. Right? And this, of course, is also can be written, if we want, in terms of this is equal to the saturation, the intensity over the saturation intensity. It's another way we've written that expression before. So this is proportional to the intensity over the detuning. All right, so that's the light shift, but what does this have to do with multiple levels? So now let's think about an atom where we have multiple sublevels. And in particular, let's just look at a sort of a simple picture of an alkali-like atom, thinking about this with an S1/2 to P3/2 transition. So we'll be thinking about this. The ground state has an angular momentum 1/2, the excited state angular momentum 3/2. We'll just ignore the nuclear spin for the moment because it adds extra complications that don't get at the essence of the problem. So we have this kind of situation where we have, say, 2 magnetic sublevels in the ground state and 4 in the excited state. So now, when we have a situation like this, what we know is that there are different allowed transitions given by the dipole selection rules that we've studied. Those are all the possible transitions, depending on the polarization of the light. We have sigma plus light, we change m by +1. If we have sigma minus light, we change m by -1. If we have pi light, then we leave it alone. And the strength of these transitions depends on the Clebsch-Gordon coefficients, which are given here. Okay? So those are the Clebsch-Gordon coefficients. So the light shift now in this problem depends on the polarization of the light. light shift is polarization dependent. One way to understand that is what we studied before, and we'll revisit that next week, is that, of course, the atom, the AC Stark shift is also equal to the polarizability of the atom times the intensity. When I have multiple levels, that polarizability is generally a tensor polarizability, which means that the light shift depends on the polarization of the light. The atom polarizes differently depending upon the polarization of the light. But we can also see that in this problem. Simply, let's look at this in a simpler picture. Let's look at the light shift for different polarizations of the light. So if I have only sigma plus light, well then the system, as far as the driving is concerned, the only transitions that are allowed are the ones that drive me from m equals minus a half to m equals plus a half, and m equals plus a half to m equals 3/2 from the ground state to the excited state with sigma plus light, right? Those are the allowed transitions. Those are these. So these are two different two-level atoms, or I can think about it. I'm saying they're two different two-level transitions. They're not coupled to one another by the light itself. And so this has a Clebsch-Gordan coefficient of square root of 3, and this has Clebsch-Gordan coefficient of 1, stretched transition. So what we can see then is that there's going to be different light shifts on the different sublevels, right? Not only is the light shift polarization dependent, but it's also spin dependent. If the atom is spin up, then it sees a transition with strength, unit strength. If it's spin down, then this strength, which depends on the square of the Clebsch-Gordan coefficient, is 1/3 as big. The atom responds with a strength 1/3 less if it's in this state than it's in that state. In particular, more quantitatively, we have here the light shift. The Rabi frequency here for sigma plus light is going to be equal to the square of the Clebsch-Gordan coefficient. The square. The Rabi frequency is proportional to, by the Wigner-Eckardt theorem, to the Clebsch-Gordan coefficient times the reduced dipole matrix element. Is that clear? That is to say, as we've discussed, the transition matrix element, if this is polarized with a certain polarization, whether it be sigma plus, sigma minus, or pi, let's just restrict ourselves right to sigma plus, the strength of the Rabi frequency depends on that Clebsch-Gordan coefficient. Okay? So that means that the saturation parameter here is proportional to the square of this Clebsch-Gordan coefficient. So that's why I'm saying this transition is 3 times as large as that transition as far as the strength of the light shift. Okay? So we have here, so we have the light shift here. let's say for, I'll just call it V for 1/2 is some the square of this reduced matrix element, the amount of sigma plus light squared divided by 4h bar delta. And for -1/2, it's 1/3 of the same thing. All right. What if I have pi light? Well, then the only transitions are the ones that preserve the m levels. And in this case, both of these have the same Clebsch-Gordan coefficient. And so the light shift for the two sublevels is equal. And it's equal in this case to 2/3 that same reduced matrix element squared, the amount of intensity in pi light divided by 4h bar delta. And if I have sigma minus light, then I derive the opposite transitions. In which case, I have that equals -1/2 is 1/3 squared amount of intensity in sigma minus light divided by 4h bar delta, and the amount of sigma plus is, no, it's the opposite. This is 1 and this is 1/3. Okay, so one point we have here is that the light shift that is seen by each of these sublevels is different, generally, and the amount of light shift depends on polarization. Lesson number 1. The other point that we discussed is related to optical pumping. So optical pumping is the process by which transitions between round sublevels due to absorption, emission cycles. So if I have our atom S 1/2 and P3 halves, then for example, if we put on sigma plus light, then the effect of that, even if it's detuned, is to absorb sigma plus, I can emit sigma plus. I'm sorry, I can emit pi sigma plus or sigma, well, I can't really, in this case, emit sigma minus, there's no place for me to go. And in the process, all the population that was originally in this state will ultimately be pumped into that state. Why? Well, because if we started population here, If it absorbs, if it falls down here, it stays there. There's no place else for it to go. If it falls back here, it has another shot. If it falls back here, it has another shot. Eventually, it falls here, and then it stays there forever, to the degree to which we have that perfect polarization. So there is a process by which not only we have coherent dynamics due to the light shift, but we also have dissipative dynamics due to optical pumping. And the dissipative dynamics occur on the time scale related to photon scattering. So the internal degrees of freedom, the ground state sublevels, their populations are changing with a characteristic time scale that's related to the photon scattering rate, which is the saturation parameter over 2 times gamma. So the light shift, we said, was the saturation parameter times delta. The optical pumping rate is the saturation parameter times gamma. And in particular, the actual rate of transition from, say, if we have sigma plus light, in this case, the rate of transitions that take me from spin down to spin up as we derived quickly last time, depends on the product of the squares of the Clebsch-Gordan coefficients for the two arms of this transition. I go up and I come down. So this is, we said this Clebsch-Gordan coefficient was 1/3. This Clebsch-Gordan coefficient squared is 2/3 times the saturation parameter associated with sigma plus light over 2. Factor of 2 times. And if I had sigma minus light, then I would pump into the spin down state with the same rate. If I had equal amount of sigma minus intensity. So the rate of optical pumping depends not only on the intensity, but also the polarization, right? If I have pure sigma minus light, then I don't pump from minus to plus, I pump from plus to minus. Okay. So, we have these key ingredients. We have light shifts, we have optical pumping, and those characteristic scales depend upon the polarization of the light. So how do we put this all together? That's the key idea. Well, laser cooling was coming from the fact that we need some kind of damping force. Why is there a damping force? Well, the damping force, we said, was some kind of velocity-dependent force. In the context of the two-level atom, what we were comparing, in order for us to get this velocity-dependent force, the question was, at what scale, what velocity scale does the atom move such that it cannot adiabatically follow, its internal dynamics cannot adiabatically follow what's going on as it moves. For the two-level atom, that characteristic time scale was related to the Doppler shift. And this sort of set the scale. This set the scale of the temperature. Whereas for the case where we have the multiple levels in the ground state, now we have a new time scale, which is the optical pumping rate. And this is proportional to the intensity. It also goes down with detuning. And as we make this time scale smaller and smaller and smaller, we have a new time scale over which we can dissipate energy. That new time scale over which we can dissipate energy is related to the time scale over which optical pumping happens, as well as the light shift dynamics. They have to work in concert to cool. And this gives us, if this is much, much less than this, which is to say the saturation parameter is much, much less than 1, that means that the temperature is much lower. All right. So, how can we make this all work together? Well, what was understood in a simple model that was put forward by Valliard and Cohen-Tanucci the idea is the following. We want to look at a situation in which there is variation, spatial variation, in light shift and optical pumping. If that spatial variation is just right, then that spatial variation can work in concert with the motion of the atom to dissipate energy. So, why would the light shift vary, and why would the optical pumping rate vary as a function of position? And the key idea here is that the polarization is varying. That is to say, they were so-called polarization gradients. Why were there polarization gradients? Well, you remember that if I looked at 3D optical molasses, there's no way that the polarization can everywhere be the same. It's just not possible. Even if I have linearly polarized in this direction, if I have light propagating in this direction, it's got to be transverse. Which means that the polarization is not everywhere the same. And we just discussed that the light shift and the optical pumping depend on the polarization. So let's get this straight in our minds. Why does the polarization vary? Let's just think about first a linearly polarized standing wave. Let's do a little aside here. Let's just think about a standing wave. Let's suppose I have a standing wave that is polarized in the x direction. So, my electric field, let's call this the z direction. My electric field as a function of z and t is equal to the real part of the vector amplitude function of z. Let's put these two fields oscillating at the same frequency. And that amplitude as a function of z is the sum of these amplitudes. So just for generality, so we can see what all the terms mean, let's say that there's some arbitrary phase. I'm not going to say what that is quite yet. It's arbitrary. Plus the counterpropagating field, which has some other phase. And the wave number is in the wave vector is in the opposite direction. So this field, what can we say about it? Well, firstly, the intensity here for the standing wave is the time average of the square of the amplitude. And that is equal to 1/2 E star E. Where this is my complex amplitude right here. So this intensity here, in this case, is equal to, well, let's just look at this complex amplitude a little bit more closely. It's easy to write this out. So let's rewrite the complex amplitude. Let me factor out the overall phase in the following way. We're going to factor that out. And this is e to the I k0 kz plus delta phi over 2 plus d0 e to the minus kz plus delta phi over 2 the x direction, where delta phi is phi 1 minus phi 2. So if we look now at the square of the amplitude, we get, well, before I do that, let me say the following. Delta phi is phi 1 minus phi 2. This is equal to e to the I phi 1 plus phi 2 over 2 times 2 E0 cosine kz plus delta phi. You buy that? So that tells me that the intensity of this field is equal to the square of this amplitude, which is equal to 4 times the intensity of one of those beams, cosine squared kz plus delta phi over 2. So if I have counterpropagating laser beams, we have the familiar fact that the intensity in this thing is oscillating with nodes and antinodes. where the distance between nodes is a half a wavelength. And what is the effect of the relative phase of these two beams?
Tells you where the, I guess where the first node will be.
Yeah, it sort of just shifts the whole pattern around. I mean, the pattern's the same, but where, I mean, this is just where this, there's a phase shift of the whole pattern. Okay, but the pattern's basically the same. So in some sense, this is arbitrary. We can choose that. We're not going to change the physics in any substantial way. I mean, it could, if we have, if that phase were jittering a lot, then maybe that's going to affect my ability to actually cool the atom. I mean, if you think about how a laser counterpropagating field might be produced, I might just bounce it off a mirror, take a laser beam and bounce it off the mirror. If the mirror is vibrating a lot, well, that's going to affect where that node is, and that might be a problem. But for assuming that we can control that, this relative phase is not that important. And so, but this thing varies from having intensity that's due to constructive interference, that's 4 times the intensity of a single beam, or twice the total intensity, and 0 intensity at the nodes. But everywhere, this field is polarized in the x direction. Okay? Now, what Dalibard and Cohen-Tanucci said was, let's look at a situation where, as we might have in 3D optical molasses, let's consider 1D optical molasses with a polarization gradient. And in particular, the most important model that really led to the modern error in laser cooling was the picture of what's called Lin-Perpelin optical molasses. What is that? Well, let's look at counterpropagating laser beams again. But let's now have them not have the same polarization. Well, yeah, let's take polarization out of the board. So in this problem, my electric field complex amplitude is equal to E0 e to the ik Lz in the x direction, plus some relative phase that we'll choose for convenience in a moment, but for now I'll just leave it arbitrary. Okay? What is the intensity at this? Well, the intensity is the square of the amplitude. And what is that in this case?
Depends on phase.
It does not.
It might be constant, isn't it?
Because there's a dot product. It is in fact constant, right? If I look at the dot product of this, I get this dotted into itself.
But if you've got the right phase, then you get circular polarized.
We will, but I didn't ask that question. I asked, what is the total intensity as a function of Z? That's equal to this. And what is it? Just take the dot product of this with itself. So that's equal to twice the total intensity. So if I look at the intensity, I'm not asking about the polarization right now. That is important, you're absolutely right, that's the whole point. But first, I want to just address the following question. If you look at this, you would say the intensity is constant. as a function of position, which it is. The total intensity does not vary as a function of position for these counterparts.
Why? If they are in phase,
Uh-huh.
then, well, they cannot really interfere, but at when one field is at 0, then the other one will be at 0 too, when they will both have the maximum at the same time. So doesn't the intensity vary then?
It does not. The total intensity does not vary, but the distribution of intensity in polarization varies, which we're about to explain, about to show in detail. I mean, one way to look at this is that I can look at this as there's a certain amount of intensity in X polarization, and there's a certain amount of intensity in Y polarization, and the total intensity is the sum of those two intensities, because they're orthogonal polarizations, and these have the same intensity. But your intuition is exactly the point, which is that this is not the full story. The total intensity is independent of position, but the way in which the intensity is distributed in polarization varies as a function of Z. So let's take a look at that. It doesn't matter what this phase is, we can choose it whatever we like. For convenience, I'm going to choose this equal to minus I. We'll come back and change it and see what it does. It will shift the whole pattern of polarization around in the same way that that relative phase shifts these nodes around. It's just a convenient phase to look at. We can choose a different one in a moment if you doubt that. So, if I do that, what is this equal to? This is equal to E0 e to the I kz Ex minus I e to the minus I kz ey. Excuse me? So I can rewrite this as the square root of 2 E0 times a spatially varying polarization vector, which is normalized. So the polarization of the field as a function of Z is equal to e to the I kz Ex minus I e to the minus I kz ey over root 2. And this is a normalized vector in the complex plane at every z. So this is the local polarization of the field at different positions along the z-axis. It is not constant. It is a function of z, as opposed to the parallel lane where everywhere this was linearly polarized. And as Cornelius was suggesting, in fact, if we look at this at different positions, the ellipticity of this field varies as a function of z. In particular, at z equals 0, well, let's just write all of this down over here. The laser field has a polarization at z equals 0, which is equal to Ex minus I ey over root 2, which is E minus, which is sigma minus if we choose the z-axis as the quantization axis. That is to say, the axis of the laser propagation. That means it's sigma minus for the atom. at an eighth of a wavelength, we have e to the I pi over 4 dx minus I e to the minus I pi over 4 dy over root 2. What kind of polarization is that? Well, the overall phase doesn't matter. I'm going to if I factor out e to the I pi over 4, then I get ex minus I e to the minus I pi over 2 ey over root 2. And that's minus I. Minus I times minus I is minus 1. So this is equal to e to the I pi over 4 ex minus y over root 2. What kind of polarization is that? Linear, circular, elliptical? It's linear, right? It's linear at 45 degrees, at minus 45 degrees. This is an overall phase shift, but the polarization depends on the relative phase between these two. So this is e to the I pi over 4 times 45 degree or minus 45 degree linear. If we look at lambda over 4, now I have e to the I pi over 2 minus I pi over 2 ey over root 2. That's I ex minus 1 ey over root 2, which is I times ex plus I ey over root 2, or I e plus minus I. This is sigma plus radiation. If you go through this, what you'll find is that then at 3/8 of lambda, it's some phase times E minus, I'm sorry, times Ex plus Ey over root 2. It's linear at 45 degrees. And then if I'm back at a half a wavelength, I repeat and I get sigma minus. So what is the picture here? The picture is the following. I have two fields, one oscillating in the x direction and one oscillating in the y direction. If the two fields are in phase with one another, you get linear. If the two fields are 90 degrees out of phase with one another, you get circular. And depending upon this relative phase, you get either linear, circular, or generally elliptical. And thus, this field has what we call a polarization gradient. The polarization varies as a function of position. We can see this in another mathematical way. Let us just rewrite this polarization vector. So before I do that, let me draw a little picture here of what we have in this field. So let me try to draw a little perspective. Here it's coming out of the board in the y direction. There's these different planes. Oh boy. Let's see if I can do it. Try. So at 0, you got circular, then we have 45 degrees, then we have circular in the other direction, then we have the other 45 degrees, then we return to where we were. Sigma minus, lid, sigma plus, lid, sigma minus, at z equals 0, lambda over 8, lambda over 4, 3 lambda over 8, lambda over 2. So along the z-axis, there are different local polarizations. We can see that in yet another way by writing this in a slightly different mathematical form. Let's express e to the I kz as cosine plus I sine. So this becomes cosine kz ex minus I ey over root 2 plus I sine kz times ex plus I ey. So this field which arose from counterpropagating cross-polarized beams is a linear superposition of two standing waves. Two standing waves, remember if we just had, when we had the just linear polarized, we had the cosine and then it was phase shifted. Now I have a cosine and a sine. One associated with sigma minus light and one associated with sigma plus light. So if I look at the intensity of this field as a function of z, it's the sum of the intensity in sigma minus and this intensity in sigma plus. Because sigma plus and sigma minus are orthogonal, so I just add the intensities. But the intensities in each of these fields is equal to 2 I naught cos squared kz. That's the sigma minus intensity. And the sigma plus intensity is sine squared kz. So that added together, you get 2 I naught. So as discussed, the intensity is uniform in the sense that the total intensity is constant. But the intensity is distributed in space such that it's a standing wave of sigma plus and sigma minus, which are phase shifted with respect to one another. So if I were to plot the standing waves, they look like the following. As a function of z, I have a sigma plus standing wave that looks just like we had before. I mean, so this is lambda over 2, this is lambda over 4. And in addition, we have a standing wave, that's my cosine squared. Then we have a sine squared. So this is my sigma plus, this is my sigma minus. So the point is, the total intensity, which is the sum of these intensities, is just equal to twice the intensity. because this plus this, the total, well, I didn't draw this so well, but the intensity is supposed to be constant if I add these two things together. If you get my drift, I hope you do. But they're distributed in intensity in polarization. Notice this has a kind of anti-ferromagnetic order. We go from sigma plus, sigma minus, sigma plus, sigma minus. So the intensity at every quarter of a wavelength is pure sigma plus, now it's pure sigma minus. Now it's pure sigma plus, then it's pure sigma minus. And it varies with the period of a quarter wavelength. In between, we have equal amounts of sigma plus and sigma minus. This is the point at which the field is linear. So this is an important picture. What we have when we have cross-polarized laser beams is the total intensity is constant, but the variation in intensity in polarization is not constant. It varies periodically. Okay, so now the next piece of the puzzle we now have this field. The question is, what happens to the atom as it's moving through this field? It's going to absorb and emit light, and we want that absorption and emission to cause us, or we expect that absorption and emission to cause us to cool. But why does it cause us to cool in such a radically different way? Well, there's a very happy accident that happens in this kind of situation. What we need to think about, first of all, is the light shift. So in this kind of field, the light shift we discussed at the beginning of this lecture depended on polarization, right? And it depended on polarization, and it depended on the magnetic sublevel. So we're looking at this Lin-Perp-Lin optical analysis, and we're looking at our atom having this level structure that we discussed at the beginning of the lecture with all these. In this case, actually, we only have, because we've chosen the quantization axis along the z-axis, we only have sigma plus and sigma minus light. There's no pi light in this field. Is that clear? Because we're choosing the quantization axis along the k vector. So we have both sigma plus and sigma minus. As, of course, we can decay with pi, but as far as absorbing, we have only sigma plus or sigma minus. So, we have a light shift on the atom when it's in this magnetic sublevel. That light shift is the sum of the light shift due to the sigma plus and the light shift associated with the sigma minus light. If we had pure sigma plus, we have the light shift associated with the Clebsch-Gordan coefficient 1. If we have pure sigma minus, we have the Clebsch-Gordan coefficient 1/3. So, what is this light shift? Well, if it's sigma plus and it's in the spin-up state, I get 1 times some constant times the distribution of sigma plus light, which is sine squared kz, plus 1/3 times the intensity in sigma minus light, which goes like cosine squared kz. So what I did was I added the light shifts associated with sigma plus light and sigma minus light. The amount of intensity in sigma plus and sigma minus depends on z. So this, where V0 here is equal to, twice the intensity over the saturation intensity times gamma squared over 4 delta. Okay? So that's for, this is the, if I just had a constant intensity of 2I naught, this would be the light shift, and then I have the Clebsch-Gordon coefficients, 1/3, and the spatial distribution. Similarly, there is a light shift associated with the atom moving spin down. That depends on how much light shift, if the light is sigma plus polarized, and there's a certain amount of light shift if the light is sigma minus polarized. In this case, this is 1/3 V naught sine squared kz plus 1 V naught cosine squared kz. Is that clear? So, let's take a look at this picture. You can write this in a slightly different form. If I write sine squared as 1 minus cosine twice the angle over 2, and cosine squared is 1 plus cosine 2 theta, blah, 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 then I can rewrite this as V naught times, I better look at my notes. I can't do this algebra in my head right now. Oh, I guess I wanted to, let me rewrite this in a slide. Let me put a minus sign in front of everything, because I'm red V2. So my V0 here is equal to to I naught over saturation intensity gamma over 4. These factors don't really matter. I guess I should, let me be more careful here. It's a gamma squared up here, and this is delta absolute value. Okay, so if I'm red detuned, my light shift is negative, right? Okay, so this then becomes minus V naught times 2/3 V naught plus 1/3 V naught cos 2 kz, and the spin down potential is equal to minus 2/3 V naught minus V naught over 3 cos. How do we understand this? Let's look at our pattern of intensity here. At the origin, I have pure sigma minus light, according to this. At the origin, there's pure sigma minus light, which means that at the origin, I get a unit light shift for spin down and a 1/3 light shift for spin up. That's what these expressions tell me. So let me try to draw that. Here's, I'll call this 1/3, 2/3, 3/3. So what do I got? I have potentials that look like this. So my variation, my standing wave variation in intensity in the polarization translates into spatially periodic light shifts, one associated with, this is my spin down potential, and this is my spin-up potential. The spin-up potential, well, it's supposed to be in line with this. I hope you'll excuse my horrible drawing. But the point is that where the intensity is pure sigma plus, I get the maximum light shift for spin-up. When the intensity is pure sigma minus, I get the maximum light shift for spin down. And these vary, it's supposed to look like exactly that pattern. Yes?
Is there only the, is there a, how do you call that, the force that breaks frictional force? Do we have that too, or is it just like a potential law where the ones that have more energy?
So right now, we haven't yet talked about the dissipative term. Right now, this part is what we call the dipole force. Now, there is, of course, the radiation pressure, but in this case, the radiation pressure is 0, because at least there would be a Doppler shift when the velocities are really big compared and on the order of gamma, but we're now talking about very low velocities. And you remember we said that frictional force only acted large in the capture velocity range related to gamma. However, we still haven't talked about how we cool in this problem. And that's the punchline of the whole story. So all I said here is there's a spatial variation in the light shift. But I haven't said anything about cooling. So the final ingredient here is optical pumping. Now, optical pumping is the effect that's dissipative. It's the effect that's dissipative, but happening not associated just with scattering photons in a certain transition, but scattering from one magnetic sublevel into another at that scattering rate, at that pumping rate. So here I am, I'm an atom. Can you imagine me as an atom? I start climbing a hill. And I will start losing kinetic energy. But you know, if I didn't dissipate, eventually I just roll down the hill and it's fine, I just oscillate. However, all of a sudden I found, oh, I really should draw this picture better, so let me try. So here we have pure sigma minus, here I have pure sigma plus, here I have pure sigma minus. Let's suppose that I'm a spin-down atom here. From a spin-down atom, I see this potential. This potential is the potential associated with the spin-down atom. This potential is associated with the spin-up atom. I'm a spin-down atom. I start climbing the hill. I start losing kinetic energy and gaining potential energy. I didn't cool. I just turned kinetic energy into potential energy. But what's happening to me? All of a sudden, I find myself in a new environment. All of a sudden, I find myself where before I was seeing pure sigma plus light. Now I'm seeing more and more, whereas originally I was seeing pure sigma minus light, now I'm seeing more and more sigma plus light. If I see more and more sigma plus light, and I'm this atom, what's going to happen to me? Well, all of a sudden, I'm going to optically pump. And when I optically pump,
not only do I change from spin down to spin up, but if I was up here, all of a sudden I'm transported back down to the valley. And I have dissipated this amount of energy. All of the kinetic energy that I turned into potential energy is all of a sudden lost due to optical pumping. Where I haven't gotten zero temperature, so I'm still chugging along. I start climbing the hill again. I'm spin up. All of a sudden I find myself in an environment where the light is more and more sigma minus. When I get near the top of the hill, I'm pure sigma minus. What happens to me when I see pure sigma minus? So here I am, I'm the happy spin up atom sitting here in my potential well. All of a sudden I see sigma minus light, and I'll optically pump the other direction and be transported from the peak of this mountain back down to the valley, where I'm again a spin down atom. And I keep doing that until I get trapped in the bottoms of these wells. And this happy accident between optical pumping and the fact that I will preferentially optically pump from the peaks of the light shifts to the valleys of the light shifts is what is now known as Sisyphus cooling. You know the myth of Sisyphus? Sisyphus had to keep rolling a boulder up the mountain. Just when it got to the top, all of a sudden, it went back, it was down to the bottom, and he had to do it again. And Sisyphus cooling is an efficient mechanism for cooling when the velocities are such that the time scale over which the atom moves over on the order of a wavelength is equal to the optical pumping rate. Because then there is this synergy between losing the energy by climbing the hills and the rate of optical pumping. And that time scale then tells me that I will capture the atoms moving at those slower rates and cool them even further, and thus get to sub-Doppler temperatures. What's the temperature limit associated with this? How cold can I get this way? Remember, the Doppler temperature was related to the line width. And that temperature was what? It was, some hundreds of microkelvins. What sets the time scale, not the time scale, but the energy scale associated with Sisyphus cooling? How cold can I get doing this? What do you think?
Depends on the light shift.
It does, exactly. It depends on the light shift. And in fact, what we said at the very beginning of class is that if I looked at the temperature as a function of intensity, it went down. Because as the intensity goes down, remember the light shift depends on the intensity. As the intensity goes down, the light shift goes down. And then I can capture lower and lower and lower temperature atoms. In addition, the temperature goes down with detuning. Let's say, as I increase the detuning, as I get farther and farther off resonance, the light shift gets smaller and smaller and smaller. And I get colder and colder and colder. Now, eventually, that doesn't work anymore. Why? Well, that's a complicated story. Let me just say a few words about it, and we'll pick it up next time. So let me just say, empirically, the temperature of polarization gradient cooling, the temperature here, is on the order of the light shift. And the minimum temperature that you get that people have measured is on the order of maybe 5 to 10 recoil energies. So the temperature that you get is, say, in cesium is maybe a microkelvin. That's pretty darn cold. The way it works in the lab is you get a mott. The mott is, detuned close to resonance. You collect all these atoms, they're very hot, and you turn off the mott, you turn off all the magnetic fields, and you put on polarization gradient molasses, and you cool down the atoms, and they get super cold. This is not enough to get to BEC, but it's a good starting place. Now, last concluding remark. This temperature was found to be so cold that in fact the temperature is less than the light shift. The atoms become trapped in the process of cooling in the bottoms of these wells. And that trapping of atoms in these periodic potentials was dubbed an optical lattice, which is a mainstay of modern atomic physics. The optical lattice was born in thinking about subdoppler Sisyphus cooling. And it was discovered that in fact the atoms were so cold that they were getting trapped in the optical dipole force associated with the molasses itself. Why is the minimum temperature hard to actually calculate? Because once the atoms start getting so cold that they get in the bottom of the wells, we have a new time scale. And that is the oscillation frequency in the well. So remember, when we were thinking about free space, there was a kind of natural time scale associated with the external degrees of freedom with the motion of the atoms that had to do with the recoil velocity. That was the time scale that we cared about. But in the context of this subdoppler temperatures, we have a new time scale associated with the oscillation as well of these atoms. And if we start turning down the intensity so far, or we turn up the detuning so much that this oscillation frequency becomes much, much bigger than the scattering rate, then our assumption that we can treat the motion of the atoms classically, but the internal degrees quantum mechanically fails. We need to think about quantized energy levels of the motion of the whole atom. The atom itself, this big chunky 133 nucleons of fat atom, is no longer just a classical billiard ball. It's a quantum fuzzy de Broglie wave, which has quantized energy levels. And one really needs to think about the quantum problem of absorption and emission of light to think about those minimum temperatures. And think about, if I start lowering this well too much, well then the 0 point energy is bigger than the depth of the well. It's a complicated story. And it was only solved, this is one of the first problems I worked on laser cooling as a postdoc. We had our theory about it. But the bottom line of it is that it's still, in my view, I just was looking at the literature last night, and I found a paper from Anders Kasberg, who was a postdoc classmate of mine back in the early 90s, mid-90s, who did some experiments about 10 years ago to try to look at the temperature relationships. What's the minimum temperature you can get to with Sisyphus cooling? And found that his experiments didn't agree with some of the numerical analyses that were done. It's still, in my view, an unsolved problem. I think empirically, this is about right. But exactly where the limit how low you can get the depth of this well such that you really can capture all the dynamics in 3D molasses is an unknown problem. But nonetheless, we can get to very low temperatures. We have these trapped atoms. And what we're going to talk about next Wednesday is the description now of these cold atoms in these periodic potentials known as the optical lattice. All right? Excellent. Have a great holiday, everyone. A good Thanksgiving. Those of you who've never had Thanksgiving, enjoy your turkey. Even those who have Thanksgiving, enjoy your turkey. And I'll see you all next week.